Landing also due to the ground effect. Dr. Lippisch, father of the Delta Wing and scientific advisor to RFB Rheinflugzeugbau, took optimum advantage of this effect in designing a vehicle known as an airfoil boat, which has strong commercial potentialities. His initial vehicle was the Mark X112, which proved the validity of the design principle. The first airfoil boat was equipped with a 25 DIN horsepower engine and was made of balsa wood to achieve its nominal weight. The aim was also to investigate the previously unsolved problem of flight stability, which was at first attempted with radio-controlled models. Here one can observe the original pitch-up tendency. This optimization process was applied to an ideal flying model of the projected X113, which was not only distinguished by high longitudinal stability, but also by automatic vertical stability. These are shots of the model on test flights over Lake Constance. Through its control capability on all three planes of motion and its banking capacity, the vehicle is able to fly extremely tight turns. Such intentional water contacts don't produce any spinning tendencies. Full circles measuring less than 200 meters in diameter could be flown at 70 knots by this 360-kilogram vehicle. Span of only 5.9 meters, it was tested in the North Sea at sea states of up to 40 centimeters wave height. We witness a takeoff from inshore waters at sea state 2. The vehicle's flight stability or automatic height holding above ground. This proves that flights, for example over ice or snow, would be feasible with no handicap to flight performance. The onboard measuring equipment at 1/20th of the wingspan, which in the automatically maintained dimensions of the X113 corresponds to about 25 centimeters, registered lift-to-drag ratios in excess of 20, human height. At the takeoff in the Baltic, one can clearly see the retracted tail wheel of the X114, which, with its retractable undercarriage, is equipped for amphibian operations. The takeoff distance of this airfoil boat, powered by a 200 DIN horsepower engine, measured about 350 meters at a sea state between 1 and 2. Its outstanding maneuverability can be clearly seen in the approach flight towards the observation ship. Its jump and turn capability, for example, from extremely low-level flight to underflight, the trouble-free transition from fast ground-hugging cruising to free flight, which requires almost the vehicle's entire engine power. The lift-to-drag ratios close above the ground are in the region of 20, reverting to 8 in free flight, which proves that the vehicle is most economical to operate when the majority of the flight can be scheduled at cruising speed and altitude. After hopping over these port installations, the vehicle resumes its optimum flying height of about 50 centimeters.
Jumping over the police.
The landing stage and jumping the obstacle only shortly before reaching it. Diving back to ground effect altitude and automatic leveling off from the pilot's point of view. Its favorable speed relative to a ship and its high maneuverability, even in tight curves, are obvious from these shots.
This is Airfish 3. Horsepower BMW motorcycle engine.
It is possible to select and control a flaring level between 10 centimeters and 1 meter. The Airfish can flare at a maximum speed of 130 kilometers per hour, whereas its economy speed is around 100 kilometers per hour. Since the drag ratio of air is about 800 times less than that of water, to move at 100 kilometers per hour, the boat needs just 35 horsepower of engine performance. With 45 litres of ordinary gas, the Airfish can travel as far as 300 kilometers, not an aircraft. No need for time-consuming flying lessons, no regular medical fitness examinations, no expensive pilot license. The Airfish can be driven like a powerboat or a car. Anybody can drive it. Operating the Airfish is easy and safe. Non-corrosive glass fibre reinforced plastic, while the wing unit consists of aluminium alloy without copper, be reduced by 1.5 meters by pivotable winglets folded in by the push of a button. The Airfish will easily glide over the waves. Its high-speed capacity enables it to evade bad weather fronts. Over 5-meter obstacles. Marshes, river rapids, spits of land, or even other vessels can be jumped by means of kinetic energy. A similar effect as experienced by a ski jumper who, thanks to his velocity, its design permits tight curves of small radii, high maneuverability. This new technology proves useful on offshore waters and large lakes, but even a winding riverbed is no problem for the Airfish. The tightest curves can be flown safely. The wing floats may even touch the water.
The first test in tow tanks. You see the front skirt.
Schluss der Versuche mit Tragwerk und Leitwerk ausgerüstet und im Seitenkanal der VBD konnte mit diesem Modell zum ersten Mal der gesamte Abwasservorgang bis zum Bodeneffektflug erfolgreich durchgeführt werden. Flügel und eine vergrößerte Tragfläche aufweist. An diesem Modell wurde erstmals das Direct Take Control System DHC erprobt, mit dem Höhenwechsel ohne Anstellwinkeländerung durchführbar sind. Die negative Einstellung der Klappen nach oben gestattet eine Erhöhung der Reisegeschwindigkeit. Die Rundlaufversuche bestätigten die Prognosen. Die Höhenänderungen wurden wie erwartet ohne Anstellwinkeländerungen ausgeführt.
We are jumping without elevator deflection. You will see it now only by the resting with the flaps. This was already the span. This means in reality 25 meters. You see how we can jump and it recover automatically when it comes to the ground.
Ein maßstäbliches Großmodell im Maßstab 1 zu 12,4 im Längskanal der VBD untersucht. Die Funktionsfähigkeit der Gesamtkonfiguration wurde in einer Vielzahl von Flügen nachgewiesen und die Ergebnisse beim Bau des Versuchsträgers berücksichtigt. Kombination von Katamaranen und Schürzen mit dem Luftaustritt in der Rumpfunterseite. Der einziehbare elektrische Hilfsantrieb im Bugbereich ist um 360 Grad drehbar. Das konnte jetzt am bemannten Gerät bewiesen werden. Bei den hier gezeigten Bildern ist deutlich das Auftauchen des Gerätes zu sehen. Messungen ergaben, dass beim Abhebegewicht von 830 Kilogramm eine Entlastung des Luftkissens von bereits 715 Kilogramm erzielt werden konnte.
We go out of the harbor only with the electrical water propeller for noise reduction and
leise und umweltschonend fährt der Hoverwing mit dem elektrischen Hilfsantrieb aus dem Hafen. Erst außerhalb des Hafens wird das Haupttriebwerk angelassen.
Start the engine when we are outside of the harbor. This is the first takeoff. Watch the forward skirt. Stop. Here's the little pilot oscillating, oscillating. This was the first flight. So the pilot tried to control. This was wrong.
In der Zeitlupe deutlich sichtbar ist das selbsttätige Öffnen der vorderen Schürzen, sobald der Staudruck den Luftdruck überwindet. Aufwendige Einfahrmechanismen sind nicht erforderlich. Der schnelle und sichere Start machte auch den Betrieb parallel zu Leistungssportlern gefahrlos möglich.
We operate between other boats. Here's the skirt again. Stop. Open. Then in the Baltic Sea.
Der Schürzen sichtbar, wodurch unmittelbar nach dem Aufsetzen das Luftkissen wieder
on landing, you will see the skirt moves forward, so you have a very soft landing. You build up and static air cushion again.
Mit kurzen Startstrecken, hoher Geschwindigkeit.
You see the vortexes in the water from the wingtip. Then some shots in Holland, which shows how stable the craft flies and how maneuverable it is between the sticks in this. In Holland they have, for the Fischer nets, many sticks, and they are difficult to find when you fly with more than 130 kilometers, so you need really high maneuverability to avoid collisions. And this is all flown hands up, with the exception of the turns there. You see here the dam, and now you will see the sticks which coming out of the water. Here. Here there's one of the sticks, here's the next one. So you have to make slalom between the sticks with 130 kilometer speed. Here the next. It's absolutely stable, you don't see any difference in height. The weight of the craft is here at the moment 1,100 kilograms, and the power is roughly 60 horsepower. And the speed is 135. The height remains absolutely constant. You will now see a landing. Oh no, it's a bypass. And please watch these little flaps on the trailing edge. These are segments which I explained later on with a direct heat control system. These flaps are spring-loaded, and they are dampers to reduce the water impact load. Very short turns, 300 meter turn radius. Another flight between these sticks and the landing. This is the dam between Enkhuizen and Lelystad in the Markermeer. This was 90 degrees turn in real time. Here you see another stick, so you make a small correction. Perhaps this was a misapproach, he had not made the landing. But have you seen, the sticks are sometimes 2 meters beside the wingtip. Here you see again the flaps on the trailing edge. This is takeoff. This is wave height 30 to 40 centimeters. And there was no problem between all these ships to maneuver, and the authorities gave us the clearance to operate between these in this traffic. Sometimes you see the intentional water contact with the wingtips. It has absolutely no influence, like water skis. Now I guess it comes to landing. This craft is again scaled down in the ratio of 3.3 to an 80-seater. So the clearance in the cabin is small, but it is 2.5 meter large. In reality, it is cabin inside is 8.5 meters. This is the dimension of the Airbus. Here you see this was a water contact with the wingtips. So when we make a very short turn, then we go with the wingtip in the water. You don't see it, you don't feel it, but you have the noise when you touch the water. Landing is only reducing the power. It has nothing to do with the controls. Now he reduced the power, and this is the flare out. And you see the skirt is moved forward, see the air cushion, and to have a soft landing. Directly beside the stick. This is a 90-degree turn.
Ja.
And the germanische Leute asked for a demonstration when we approach another ship. And we have to go parallel a distance of 50 meters. The noise level is 65 dBA in 50 meters distance. Here they ask to avoid a collision. We are arriving with 125 kilometers speed. The points are measured points with GPS. So you 107 meters in front of the boat. We make a turn, go around the ship. So we have the chance to go beside an obstacle in a distance from 170 meters when we have 125 kilometers. This was one. Now we go back to the
Das ist das Ausweichmanöver.
This gives an impression from the right quality. The camera is installed on the tail, and you see absolutely no acceleration, zero heat. This is the turn. No risk of any seasickness. Landing 20 meters beside the boat. And you see how the flaps are moving, reducing the load. And this was our last flight. The German Leute asked to show what happens when we have to land with the aircraft in 3.5 meters wave, taking 2.5 meter wave. Here we have 1 meter wave. It means AERO 3.5 meter range. And we landed under this condition, without any damage is and this is some shots from our first flight, with Flight 8 in Holland in February this year.
Was
You see the undercarriage, can retract the wheel to go on land. Take off weight 4,100 kilograms, installed power 450 horsepower. This is here the first flight. Unfortunately, it was in February. It was very cold. First test.
Machen wir ein Foto. Komm mal näher ran, das war toll.
War gut,
Also
ja.
Anni,
Am Schwank gehabt, ja.
der ging so vorne auf der Nase sofort hoch. Also die
Klaus, wie geht es heute?
Ich weiß das auch nicht. Ein Weberknoten kennen wir.
Weberknoten.
It's all built in composite, template, combination with glass fiber and carbon fiber.
okay.
The aircraft is now in Australia for
Wieder
license
dahin.
production.
Ja, wieder an dieselbe
28
Stelle.
persons, 750 kilogram payload.
So, jetzt kriegen wir das
And
mal
it
alles auf.
is built under control from the German Lloyd.
Ding in der Luft. Gar kein Problem. Lenker Anflug.
Already on flight number 2 we started around the observation station. We were able in 2 days to fulfill, to demonstrate all the required data, and the customer has accepted that all specifications are 100% fulfilled.
Fotografieren, ja? Ja.
Where we need roughly 300 horsepower for 1,100 kilograms per day. Flight number 4. Now on the end you will see the landing and the long flare out and before touchdown on the water surface. Here we have waves roughly 60 centimeters. The requirement asks to fly with 175 kilometers per hour over waves of 2 meters and the range of 350 nautical miles. You can also watch that it is absolutely stable. You see constant wind. Heads up. Now the landing and the long flare out. Power is at 0. Flies and flies. Come closer to the ground.
Jetzt hat er schon gesehen. Ja klar. Vorbei. Ja, ja.
And still with engine out. Also it's idling.
Ja, der landet. Jetzt ist es wunderbar. Super. Touchdown.
Hä? Weer Leitwerk? Ja, nee, oké.
Yeah. Geez, that wasn't even 30 or 40 meters.
So thank you very much. I hope you have a first impression what we can do. You have now the coffee break? Is now the coffee break? Oh, what's going on? It was not easy to get a clearance from the Germanischen Leute. They came all 8 days to watch and to control the production, and we have built a test rig with the engine and the 2 propellers to run 50 hours to simulate all conditions to avoid modifications when we are in testing. So it is always better you test each components before, and then you are fairly sure that on the end everything works. And otherwise you work with temperature of the engines and vibrations and many things. So it's better you test every component before, and on the end, like on aircraft, and on the end it remains only hydrodynamic and aerodynamics. Yeah, please.
How did you get the idea of this inverted delta design?
What is it?
How did you get the idea of this inverted delta design for the Airfish?
Lippisch. Yeah, it is the old Lippisch design. It is in principle a scale up from X113, X114, and then Airfish 1, 2, 3. And so this is all scaling and optimization in small steps. Our next step is a 20-seater. So in principle it is better, especially when you have such an unknown situation, better to make many small steps. Instead, make one step too big and you end up in a disaster, then you kill our ground effect idea.
Process, do you work with models and equations, and so you can sort of predict how the plane will fly? Or do you use models or both?
In my presentation, which starts now, when I know if we start now or after the breakfast, I will explain you and show how we do it. We try with a lot of testing, and I will give some information about that. To make sure that every step is okay. And in principle, we make the calculation first, and then the verification with tests. Aerodynamic test, wind tunnel test, tow tank test, model testing in round circuit, and so step by step, we verify that the theory is right. In the presentation, you will see then the approach how we do that. So we install in the model a lot of test equipment.
Oh. Well, I will be very pragmatic. Could you tell us how long it takes to build the prototype. I mean, once the studies are finished, or...
You mean the timing?
Yeah.
Yes, we received the order from a group in Australia, Singapore, to build this 8-seater, and there is a very strong specification. It tells payload, it tells volume, it tells range, noise, and everything. And after that, we started the design, also model testing again, and the whole thing was 3 years, from receiving the order to the delivery of the craft. The production is roughly 50% of their time, and the development and testing and all, let me say, necessary steps is the other 50%.
Thank you.
So we are now really able to offer a customer the guarantee that we deliver the required performance when they are logical, clear. But this was the same with the Hoverwing. We have received the specification by the government, and in my presentation I will show the results. And then we had to show that every point of a big book is fulfilled.
Okay, one more question.
Please.
And from the customer's point of view, could you tell us about the purchase cost, or the cost you sell to customers? What would be the cost for customers?
Price. Good question. Price is always a question how many craft you build. You see, we have this learning curve. There are some thumb rules. The thumb rule says when you build on aircraft, I am aircraft designer and producer. Normally the thumb rule says when you build 100 craft, the first craft costs roughly 12 times the price from the production. And then you go up with a learning curve with this degree of 82% roughly. So you collect with the prototype a lot of money. The amount of money to develop that from zero to delivery is in the area of 5 million Deutschmark, or 2.4 million euro, or euro in future, or dollars.
Thank you.
The production version, the price is around $750,000. This is roughly a third of the price in comparison to an aircraft, same seating. Price per seat in aircraft versus ground effect is roughly 1 to 3. So the economy is much better. Again, if we remain under 1,000 kilometer distance, then aircraft has advantages.
Okay.
You say that you receive order from Singapore. Are you aggressive, commercially speaking, or just waiting customer? What is your politic, your commercial strategy?
Our politics?
Yeah.
Yes, we are looking for customers, clear. We have gained the know-how, and my definition of know-how is nothing else than to have the chance to make a lot of mistakes and not to repeat. So we had made a lot of mistakes to learn, to understand what Professor Rodoswensky have explained, to convert it in real world, in hardware. So this we try now to bring to products. So the next is a 20-seater, but I have to explain the Airfish is first generation, without and takeoff 8. And the second generation is the Hoverwing technology, which I have explained, which has the advantage that you reduce much less power, install much less power to overcome the hum speed. This is the main key. We have seen yesterday from our colleagues in Russia how many horsepower or kilowatt you have to install to overcome the hump. I think the answer was yesterday the lift to drag during takeoff was in the region of 3. Professor Rostoswensky, no? And this is the price which you have to install. It's money, is weight, and it costs payload on the end. So the answer for commercial use is to reduce the installed power to a minimum.
And,
take off it.
And maybe my last question, what are your competitors?
Yeah, I can...
Who are?
Yeah, many, mainly aircraft. The requirements came from a question in the Maldives. They're arriving every day airliners with roughly 300 to 350 tourists, and they have to bring these tourists to the 50 islands around. The islands are between 20 kilometers and 300 kilometers. So when they go with the boat, the distance of 300 kilometers, this takes longer than the flight from Europe to go there. So in the moment they make it, they started with helicopters. Helicopters cost a lot of money. They were mainly Russian helicopters, and spare parts are not more available, and they claim the hotels it is very noisy. Now they are using mainly Cessna Caravan on floats. They had also 2 accidents already, and it's also expensive. So on long terms, this is a competition, a seaplane or float plane. But on long terms, we will replace, and this is our intention, these crafts, which 30% of the price. We have not redundancy, we don't need a pressurized cabin and all these things. We are all the time over the runway, so the price is on the end better, and you remember my presentation merit factor, so we can compete against airplanes under this condition. Okay?
Mario Michalina, Zagreb. Can you tell me what do you expect as a worst accident with this craft when you are using this craft? As we saw yesterday on the models, there is some problem when it is a problem because when we travel with the ship, if you know he is sinking, we can put the SARS and jump in the sea and swim, but it will be quite, maybe it will be scared of the people when this craft will have an accident, what is
can happen.
Yeah. You know, it will be a very short time, you know, it will just pitch down something.
Yeah,
so
I understand the question. It's the same question with all our authorities, especially the German authorities, are asking. The main point is to have absolutely natural stability. With natural stability, we understand that the craft don't depend from electronics or any other helps which can be critical. And we have to show that we are able to land in 2.5 meters, also in an area where the waves are not higher than 1.5 meters, to have a reserve. And then we have to fill all the requirements from the IMO and SOLAS with all the boats and so on. And so we say that normally we can be sure that we have no accident, we had never a pitch up, and that is the reason that we make so many testing before. So I think this is not a question. The biggest problem will be perhaps a collision with other craft. Then the boats are going with 20 kilometer or 30 kilometer speed, they are standing still. And we have the faster craft has always to give way to the slower. This is a rule. So this was the reason that we have to show that we run with 170 kilometer speed. And here is the observation ship, make a pass with a distance of 50 meters to be sure that we have no collision. This is one point. The other point is when you have bad visibility. So they ask now for radars. But the marine radars are things like that. These are air brakes you can't use. And there are in a moment big discussions how to arrange the clearance that we can operate. We will operate in next summer in a demonstration route from Lübeck to Warnemünde to Rostock to Stralsund. We will do it many times per day with the government people on board to show that it is a safe route. And what we work in addition, I can tell you that we are trying now to install a kind of braking system as an emergency stop. And you go around an island, I've flown in Miami and go around an island, suddenly was a race boat in front of me. But this was small, I could jump over. But when it is a big tanker, I can't. So you need an emergency stop. And we are developing now such an emergency stop which give you a 1.1 G on braking. This is similar like in a car when you go full on your brakes. And then we will stop in the distance when we come with 180 kilometer speed. We have to stop in 400 meters. And then we are working now on artificial things like radar, and there was some laser and so on, that the detection range of an obstacle is then longer than the 400 meters. Then we are safe against collision.